Hi guys, we are going to start our module number 5, that is analysis of beams. Okay, this is fifth module. What we need to start, that is analysis of beams. Okay, uh, before going into this beams, we need to know some basics which you have already studied. You can see I have written a diagram here. This is a bar and this is a beam, and this is a cantilever beam if I want to be specific, and this is a simply supported beam. Okay, in FEM, if you look at that might be analysis of bars, that might be stepped bar, or analysis of bars, or trusses. See, our aim is to find out the displacements first, that is nodal displacements Q. Based on the nodal displacements only, we are going to find out the stresses, strains, and as well as reactions. Okay, generally in our FEM there are two methods for finding out the unknowns. Means that unknown might be stress or strain or reactions or whatever it might be. One is a stiffness method. Okay, one is a stiffness method, other one is a displacement method. Okay, we generally, whatever the chapters we have discussed till date, okay, on all that we have studied the displacement method. Means you need to find out the displacement first, later you're going to find out that might be stress, strain, or reactions. Okay, so this method is not widely used. Okay, we generally use the displacement method at a greater scale compared to a stiffness method. Now, what do you mean by a beam? That is a basic definition you need to understand. What do you mean by a beam? Okay, what do you mean by a beam? There is one small difference between a beam and a bar. A beam is a structural member which carries transverse load. If you look at this, see, the loads are acting at an angle of 90 degree. If you look at the bars, the load is acting along the axis, or along the axis of the bar, the load is going to act. That is a major difference. A beam is a structural member which carries transverse load. Okay, which is going to carry transverse load. Um, so this transverse load means 90 degree. Now, as I told you, we are going to find out the displacements first. Later, we are going to find out the remaining unknowns. Before going into this module, see, whenever we are going to do the analysis of beams, our basic requirement, generally what we used to do in analytical method, that is analytical, or the one more name is classical, or using in your SOM subject or in your MOM subject, what we used to do is we always used to concentrate more on our shear force diagrams and bending moment diagrams. In other words, we are going to concentrate, whenever we're going to do the analysis of beams, we're going to concentrate more on shear force diagram, bending moment diagrams, and all. Later will be our bending stresses. Okay, and we are going to find out all these unknowns, that might be shear force diagram or bending moment diagram on the bending stress, first finding out the nodal displacements or the deflection. Okay, generally when it comes to the beam, we never call it as displacement, we call it as deflection. Look at this, this is a initial position. Okay, when the load is going to act, it will be deflected from its mean position. So generally we used to call this y, whatever the y I am showing, that will be generally called as deflection. But when we are going to solve the problems with the help of a finite element method, we generally call it as nodal displacements. Okay, now compare these two figures. In these two figures, you can look it out, you can look into these figures. Okay, my load F, which is going to pull the component. So thereby pulling the component, the nodes are being displaced along which direction? The nodes are being displaced along the x direction. Okay, now if I try to write the coordinate system, okay, according to solid mechanics, if a body is displaced along the x direction, the displacement is represented by the symbol u, and this is y direction and this is z direction. Okay, u is the displacement that is generally utilized in order to represent the displacement along x direction. And if any body is displaced or any node is displaced along the y direction, the displacement will be indicated by the term v, and along z direction we are going to consider it as w. U, v, w are the displacements along x, y, and z directions. Now look at this. Now look at this figure. There is a cantilever beam. One end is completely fixed and the free end, it is subjected to force F. This is very much important because when you want to solve the problems, the type of displacement is a major role. Based on this basics only, we are going to build the shape functions or the stiffness matrix. Now look into this. This is a cantilever beam. One end is completely fixed, whereas the free end is subjected to a force F. Now what is going to happen? Due to this force, now let me create a finite element model. So what I'm going to do is I'm going to drop the lines from the ends. I'm going to place nodes at the ends. Okay, so this is node number 1 and this is node number 2. This is one element. When the force is going to act at node number 2, automatically node 2 will be displaced from its initial position. So that displacement is given by V. Able to understand? That displacement is given by the symbol V. Okay. Now that our node is displaced along a y direction, that displacement is given by alphabet V. Next, you can see what is, I am written something here, that is theta 1. What is this theta 1? See, the force which is going to act at this end induces a bending moment at this fixed end. Okay, that is bending moment MB will be given by force into perpendicular distance L, if L is the length of the beam. Okay, due to that bending moment, what is going to happen for my node 1? It is not going to be displaced. See, my node 1 is at this location itself. Okay, but it is not being displaced, but it will be rotated about an angle. Okay, that is one more type of displacement you are going to concentrate. Since it is completely fixed, you can't tell it as theta 1. Let me come to this one. Okay, it is a simply supported beam. Okay, due to this forces, okay, due to the force F, you have seen a linear displacement along y direction, that is indicated by V. And since it is simply supported at this point, okay, if I place a node at that point, due to the bending moment at these locations, okay, my node 1 and my node 2 will be rotated by an angle theta 1 and theta 2. So these are the type of displacements what we are going to get in our beams. What are those means? One is a linear displacement V, other one is a angular displacement theta. Okay, so this is a basic of a beam. If I try to write a beam like this, okay, generally representation of beam, how exactly we're going to do in our FEMS, if this is a beam element, this is node number 1 and this is node number 2 and this is element number 1. Okay, node will be having a linear displacement, okay, that is indicated by the upward arrowheads V1 and V2. That is a sign convention what we want to take. Okay, since it is moving towards a positive y direction, okay, that is a sign convention, because positive upward is a y, downward is a negative y. So in order to show the positive sign convention, we are going to show the displacements in the upward directions. And now we are going to show the angular displacements theta 1 and theta 2. Generally, we are going to take this angular displacements theta 1 and theta 2 in the counterclockwise direction. That's a sign convention. Okay, counterclockwise direction, which is positive. If it is acting in the clockwise direction, then obviously it is negative. See, you need to understand one more thing. Here, V1 and V2 are the linear displacements, which is due to the forces F1 and that might be forces, transverse forces F1 and F2. These theta 1 and theta 2 are the angular displacements, which is due to the bending moments M. Okay, there is this major thing you need to understand. Okay, the linear displacement, nodal displacements will be happening due to the transverse force, and the bending moments due to the forces causes the angular displacements. Okay, this is a major thing what you need to understand about the analysis of beams. So beam element, how many degrees of freedom it consists? 4 degrees of freedom. Among these 4 degrees of freedom, V1 and V2 are the linear displacements. Theta 1 and theta 2 are the angular displacements. Okay, so there are 4 degrees of freedom. Now, our next basic thing, or the next essential thing, is to find out the shape functions. Okay, see, generally Hermite shape functions is very widely used, okay, for beams. Hermite shape functions for beams. Okay, Hermite shape functions. Next, we're going to start with this derivation. Okay, before going to it, I'm going to just rewind it. Generally, what is a beam means? A beam is a structural member which carries a transverse load. Okay, a load which is going to act at an angle of 90 degree. okay, to the axis. And in a beam, there will be two types of displacements. One is a linear displacement, other one is an angular displacement. As I told you, the linear displacements will be due to the forces F, which is acting on that. At the fixed ends or at the supports, you're going to get the moments due to the same forces, that is M moments. That moments causes the angular rotation of that nodes. Okay, that angular rotation is given by theta 1 and theta 2.